So we've got an LDR rated at 2 mega ohms, and the LDR is a light dependent resistor, changes resistance depending on the light, and 10 k ohms in the light. It is used to be, let's make sure we can note those two, light and dark. It is to be used as a refrigerator warning sensor to light a lamp when the door, I shouldn't have drawn over the top of that, inside the door, there we go, when the door is open, and to switch the lamp off with an electronic circuit when the door is closed. To perform the sensing, the output voltage across the LDR has to rise from exactly 0.5 volts to over 3.0 volts as the door closes. Okay, so this is a tricky one. A is draw a suitable potential divider circuit and choose the value of the fixed resistor that allows the specified voltage change. The electronic circuit has a supply of 12 volts. So I think the best thing to do to answer this circuit would be to draw it out. I'm going to draw it slightly sideways because it's easier for me to imagine the voltage divider circuit that way. So we've got two resistors. One of them is our LDR and one of them is our fixed resistor. And so our aim is to go from 0.5 to volts across the LDR to 3.0. So 0.5 volts will be in the light and 3.0 in the dark. Is that right? To over 3.0 as the door closes. So yeah, so in the dark you'd assume it's going to turn off and that the light itself is not going to affect the resistance of it. In any case, the resistances have to change from, in the light, 10k ohms to 2 mega ohms. So that's 2 million, 2 times 10 to the 6. So now all we have to do is use the values that we know to find out our R values. And so we know if there's 0.5 volts across the 12 volt, there we want to have from a 12 volt supply 11.5 volts across there in light, and in dark has to be 9 volts or less, 9.0 volts for this resistor here. Okay, so we know the voltage ratio now, and we have the resistance of the LDR at each point. All we have to do is put that into an equation to work out what it will be. And the equation that you would likely use is same thing here. The voltage across the resistor is equal to the voltage across the supply times by the value of that resistance over the resistance of the LDR, depending whether it's light or dark, plus the R value itself. So what you'd have to do is put in the values you know, which is VR, you know VR, you know VS, you know VL, R, LDR, the resistance of the LDR at each of light and dark, and rearrange for R. So there'd be a little bit of rearrangement and solving, which is more mathematical skill, but I think that covers how you do this question anyway. That's just the setting up. And remember, you have to do it once for light and again for dark. And you have to make sure that your value of resistance R is going to be suitable for both of those. So perhaps you'd have, maybe you'd need to do this as a range actually, that could be a good one. So VR has to be, well yeah, I'll just try this, try it for a value, throw a value in and see how it goes. Yeah, a little bit of trial and error, but that's not going to be too tricky. But you could also base your, once you've done both extremes, you'll be able to choose one that's going to fit both. Because as long as it goes, brings this one to below 9 volts, then you should be right, and as long as in the light it's okay. But if you have a look at this, the range 2 mega ohms to 10 ohms is about 200 times. Is that right? Yes, it's 200 times. So you have to choose a value of the resistor R that allows for 200 times change in the resistance there. but it's only for the voltage change. The voltage change is only, for the minimum voltage change anyway, is only 6 times. I should really put times 6, but and that means that if you choose a value of the resistance that matches this change 6 times, then you're almost certainly it's going to be fine on here. Okay, have a play with that. I think that gives you plenty of ideas to work with.